Hello! In this video, we are going to prove the following theorem. For all positive integers n is greater than 0. Okay, now the book I'm referencing is Intro to Real Analysis, 4th edition by Bartle and Sherbert. And in proving this theorem, we're going to rely on two facts. The first fact is that for every non-zero real number a squared is greater than 0. And in the book, this is referred to as Theorem 2.1.8a. The second fact is that for every two real numbers, a and b, if a is greater than 0 and b is greater than 0, then a plus b is greater than 0. Okay, so now let's get into proving the theorem. And we're trying to prove a statement about all positive integers. So we're going to use induction. So let's start out with the base case. In the base case, we're trying to prove that 1 is greater than 0. And to prove that 1 is greater than 0, we're going to apply fact number 1. Now, we know that 1 is a real number, and we know that 1 is not equal to 0. So since 1 is a non-zero real number, fact number 1 applies to 1. So we have that 1 squared is greater than 0. However, 1 is equal to 1 squared. So since 1 squared is greater than 0, and 1 is equal to 1 squared, we have that 1 is greater than 0. So we have proven this statement in the case where n is equal to 1. So we've proven the base case, now we're going to move on to the induction step. Now in the induction step, we give ourselves an arbitrary positive integer n where this holds. So let n be any positive integer where n is greater than 0. And the whole goal of the induction step is to prove that n plus 1 is greater than 0. Right? We want to prove that this statement is also true for n plus 1. Now, we know that n is greater than 0. And from the base case, we also know that 1 is greater than 0. So since n is greater than 0 and 1 is greater than 0, we can apply our second fact, right? If we call capital A n and we call capital B 1, well, we have that a plus b is greater than 0. In other words, n plus 1 is greater than 0. And that's exactly what we wanted to prove. So this completes the induction step. Therefore, this closes the induction. And so this completes the proof. And so yeah, that's pretty much it for this video.